Okay. Okay. So it's recording now, right? Everyone can see that.
Yeah.
Yeah. Okay. So Sania, can you restart again? Thanks.
Yeah. Hi, I am Sunil. I'm a postdoc in the Minnesota Dental Research Center for Biomaterials and Biomechanics. This is in the School of Dentistry, and I work in the Moose Tower building, essentially on dental materials and on similar devices.
Okay. Thanks. So Gaurav.
Hi, I'm Gaurav Nayak. I am a final year PhD student in the Department of Mechanical Engineering, and I primarily work with atmospheric pressure plasmas and their interactions with liquid droplets and certain applications, which I'll discuss today. Thank you.
Okay, I look forward to your area because I think I'm relevant to that.
Yes, yeah.
Okay, Julia? Julia.
Hi.
Okay, sorry.
No, it's fine. It's fine.
Yeah.
I'm Julia, and I'm working at the Department of Medicine, Division of Cardiology. So the group of Dr. Jean Ochi, we focused on mitochondrial disease or mitochondrial dysregulation in cardiovascular disease. So, and now we just expand a little bit our area. So we try to figure out how COVID will affect this. So, yep.
Okay, that's great. So before we start the presentation, the IEM side want me to go over these two slides. So it's a little bit different from the traditional annual conference. You know, traditional, you have a real poster in a big room and everyone can see all the posters. This time, because of the pandemic, is different. So we become many small sessions. So as you can see, not too many audience can come to see your work, but we only have you here. So the goals become different. Is we try to bring IEM research labs together by this forum, and also we try to help all of you to develop communication and collaboration skills. So I'm the faculty facilitator, and my job is to help you know each other's work and if possible, think about how could all of you collaborate together to create some unexpected opportunity and to address some pressing issue, either it's COVID or something else. Okay. And as I mentioned, we recording the sessions, and I will have to upload the recording to the annual conference. Then everyone can see it because you know, this is a small session, others cannot see your work except everyone in this session. After we upload the recording, if other people are interested in your work, they can come to our recording. Okay, that's for these slides. And next one is we actually have a competition. It's called the IEM Pilot Project Competition. Essentially, it allows 2 or I would say 3 poster presenters from different lab or even same lab should be fine, and to work together. And IEM have some funding. It's small, but we have some funding, $5,000, and what you need to do is a 2-page proposal, and 2-page doesn't include the reference and biosketch. Then after the proposal, you have the reference, citations, biosketch of each one. I think you should follow the standard NIH biosketch template. I think a 2-page something, I forgot. Okay. And the proposal deadline is October 12. And if you want to do that, 5 p.m. And there's more details in this link. Okay. And the review panel will be formed to review all the proposal received. These are small seed money. Just try to push out some collaborations. Okay, it's not supposed to say support a student or postdoc for a half year or more. That's not the case. Okay, that's all I need to say. It's already 1:02, so let's start the. I'll stop sharing. Then you can let me allow to share. So let's start the presentation, starting from Sunil. Follow the order of last name. You can share your screen and do the presentation.
I'm just sharing my screen. Yeah. 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 Hello, everyone. Today, I'll present briefly on my recent a small approach towards COVID-19 detection. So this is actually a piece of work which took off from my earlier project, wherein I developed oral tissue adhesive membranes for oral biosensing and also for delivering some small oral therapeutics such as antimicrobial peptides. So here I'll talk on using similar intraoral membranes and also some design of intranasal devices for COVID-19 patient sampling. So I think we are all familiar with the CDC guidelines for patient sampling. So essentially, you swab the patient in the nasal cavity and in the oral cavity. So that's deep in the nasopharynx region, deep into the nose, or deep in the throat, the oropharyngeal region. So those are the locations with maximum abundance of this virus. And later on, they also modified the guidelines to include even the anterior nares, the nostrils, and also the mid-turbinate, the middle portions of the nasal cavity. Those places could also be swabbed to collect the virus. And you can see that these are the different designs of the swabs. The first ones which came out from Copen Diagnostics, they have a plastic sample applicator with the end having a nylon or polyester or rayon fiber mesh to collect the virus. And the other type of diagnostics are the salivary diagnostics, like the one which was developed by the Rutgers Dental School. So you just put in your saliva in the tube and send it for diagnosis. So the problem with this kind of COVID sampling, like deep in the nose or in the throat, is that it causes a lot of patient discomfort. If you have actually had the test or if you have seen it, you would observe that uh, you can only sample for a very short time, and the sample collection is critical to getting a positive or negative result. And that is what I'm trying to address by having these wearable devices. So if you have an oral membrane, just put it on the teeth or the gums, and whatever virus which is circulating in the oral cavity can be electrostatically captured on these membranes. So from what I gathered in literature, these virus particles have a small negative charge on their surface. I have actually even measured it. So that can be captured on cationic polymer membranes in the oral cavity. Similarly, I have also come up with a design for intranasal device. So this is again inspired from the silicone based devices they use for treating sleep apnea. So these devices actually cause nasal dilation and help in better breathing. So that's how they work for sleep apnea. But I thought that they could similarly be modified to, to surface coat them with these kind of cationic polymers, so that whatever virus is present in the as aerosols in the air, could be trapped electrostatically onto these devices. So this idea, we have recently patented it, and just filed it. And coming to some of the results very briefly, since these viruses are BSL-2 type viruses, so the virologists, typically our collaborator, they use a technique called pseudotyping, wherein they produce these virus particles by transfecting cell lines, normally the human embryonic kidney cell lines, 293 T cells, with plasmids encoding for the few of the viral proteins. Here we chose the HIV-1 lentivirus, and also the plasmid encoding for the spike protein. And this is just a small characterization of these viruses, how they look under the TEM, and and also the Western blot for the spike protein. So we had two types of particles, one without the spike and with the spike protein. So if you have read about the spike protein structure, so it's a trimeric protein, and each of the monomer subunit has a size of 180 kilodalton. So that's a very faint band. I'm not sure if you're able to see that, but they are still optimizing it. And you can also have different amounts of GAG to spike protein expressed in these particles. And I went on to check with the dynamic light scattering equipment, the size, the hydrodynamic size of these particles, as well as the surface charge, by making the zeta potential measurements. And we could actually detect a considerable small amount of negative charge for both the types of particles, with and without the spike protein. And then on the right side is the scheme of experiments, wherein I co-incubate my polymer membranes with these virus in cell culture supernatants or physiological phosphate buffer for certain durations of time, let the virus adsorb on the membrane, and then desorb them by the regular technique of centrifugation to detach all these viruses from the surface, and then analyze them with ELISA. So here you can see this is a typical nanostructure of the membrane that I have designed. It's composed of chitosan, but you could have any other polymer membrane without these kind of nanotopography or structures. I just did that to increase the surface area, and then I was able to image the viruses. I mean, these are aggregates of the viruses adsorbed on these membranes, and the viruses are labeled with the fluorophore M-cherry in this case. And then I desorbed these particles into viral transport medium, and then analyze the ELISA for the for the desorbed particles, as well as for the remaining of the viruses in solution. So I was able to detect with ELISA with whatever arbitrary conditions I started off, because I'm trying to have concentrations of viruses which you would typically find in the oral cavity. So that's the main idea, to have a concentration to assay different concentrations of these viruses and see what's the detection limit, and also to optimize the incubation time. Shorter time would be better in principle. That's the goal of this project. And I would like to acknowledge the funding source for these pilot project that we are doing in our lab in collaboration with people from the Institute for Virology. And this project is funded by the CTSI, the Clinical and Science Translational Institute, University of Minnesota, with myself as a co-investigator on this grant, because I came up with these ideas on what we could do from our lab to address COVID. And also the other collaborator, Louis Mansky, their lab personnel, for helping with the virus particle production, characterization, and also discussions, because I'm not a virologist myself, and the technology commercialization office for helping us file the initial patent, and the characterization facilities, and also Professor Vishan for letting us use their facility to make our membranes. So I think with that, I'm finished and open to questions.
Okay, thanks for the nice presentation. Because we only have three presenter in this session, so I allow you to go a little bit beyond. Any questions?
Sunil, that was a very nice presentation. I have one question regarding the charging of these virus particles. You said that you measured those charges on particles?
Yeah, so you can actually measure, like for regular metal nanoparticles with the DLS, you can measure the surface zeta potential, right? So in a similar way, I took the cell culture supernatants in which these virus particles are suspended, and I carried out similar measurements for the size as well as zeta potential. So I could detect negative values close to -10 millivolt, which is not as negative as I would want them to be. So if they have a more negative charge, that would actually, help achieve my goal in having those electrostatic mechanisms to concentrate them onto these devices.
And do you think that these charges are before you have this electrostatic charging or after it is electrostatically charged?
So they have the charge by themselves. So it's not like I do something to create some charge. Like
Okay.
I'm guessing, like if you're saying, like if you're doing some kind of oxygen plasma treatment, like in your case, so you generate some kind of surface polar groups, and you
Yes.
might be generating negative charge, right?
Yeah.
So this
Yeah.
is not that. This is the
Okay.
inherent charge of these particles. Like even bacteria also have some amount of negative charge due to negative surface groups in those proteins.
Yeah. Okay. Thank you.
Any other questions? Julia?
No questions so far. I just want to say thank you. It's a very good presentation, and I'm impressed. Yeah.
So the size you mentioned, the nanometer, is the virus size or the aerosol size is attached to?
This is the virus size. This is like the hydrated virus in the buffer or in the cell culture medium.
Okay, yeah. For the sake of time, let's move on to the next one. We will have a very long time discussion among all of you after all the presentation. Okay, so Gaurav, go ahead.
Just a moment, I'll share the screen. Let me see the tool. Just a second. Okay, can you see my screen now?
Yeah.
Yep.
So your advisor is which one?
Peter Brugman.
Oh, okay. You're Peter's student. Okay.
Yeah.
Okay.
Okay. So good afternoon, everyone. And the poster I'm presenting is based on our research on the inactivation of aerosolized virus by plasmas in air at atmospheric pressure in timescales of milliseconds. So that's why I call it rapid inactivation. So as we already discussed, this virus outbreaks are a major worldwide concern, which is clearly evident from the ongoing COVID-19 pandemic, which has already claimed 1 million lives as of September 27. So when we first proposed this study, it was basically for virus outbreaks in animals and birds, such as the 2015 avian influenza outbreak and the 2005 first virus outbreak. But this work might be even more relevant in the current situation. So the state of the art Mitigation technology for these kind of virus includes use of highly efficient MERV and HEPA filters in conjunction with the HVAC system. That's with the centralized air systems in buildings. However, with continued usage, the pressure drop across these filters increases significantly, and this reduces the performance of these filters. Moreover, the virus can remain active even when it is trapped in those filters, and it can be re-released into the atmosphere during replacement of such filters. And these filters require regular replacement from 6 to 12 months period. So an alternative technology or technique is to use air-based electrical discharges or simply plasmas, which are basically energized gases containing a mixture of neutral species, electrons, ions, and excited state species. So since Sunil discussed this of the charging, I wanted to say that these electrons, they move faster because of their low mass. So they attach to these virus particles or the droplet particles, and that's how we get the negative charge in our plasma. So in our earlier research, which I'm showing here, we have shown that plasma was able to inactivate some heat-sensitive surfaces like Roman lettuce leaves or even chicken surfaces. And this was done on a time scale of few minutes. But when we consider the virus in the form of aerosols, the bigger challenge is to inactivate these particles in time scales of milliseconds, which is 3 orders of magnitude lower. And this is very similar to typical air residence times that we found in our HVAC systems. But very few studies have been done in this regard. I think 3 or 4 studies from US and Europe. And I think that this kind of plasma-based disinfection technology has both academic potential as well as industry scope. So for our experiments, we used a single pass test tunnel or a wind tunnel, which was designed to operate at high volumetric airflow rates. We used HERS virus, which is porcine reproductive and respiratory syndrome virus, as the target virus, which basically affects the pigs. So the virus solution was basically aerosolized using an atomizer, and these aerosols were carried by the airflow inside this tunnel through the plasma reactor, which was embedded inside this tunnel halfway through. So we did aerosol sampling both upstream and downstream of the plasma reactor in these bio impingers, and this contains some kind of protein-rich solution, for example, DMEM. So these aerosols, they are in direct contact with the plasma for a short period of around 15 milliseconds. However, after exiting the plasma reactor, it takes 3 seconds for the aerosols to be collected in the downstream impinger after treatment. So the shorter time scale here basically determines the effect of short-lived reactive species produced by the plasma, while the longer time here determines the effect of long-lived species such as ozone or hydrogen peroxide. So the plasma reactor that we used in the study is commonly known as a volumetric dielectric barrier discharge, and we ignite plasmas in these rectangular slits here by applying a high voltage AC signal. We used a constant frequency of 26 kilohertz, and we changed the duty cycle operations to which allowed us to operate the plasma at different average powers. So we can go from lower power to high power and see the effect that it has on the virus inactivation. So here I am showing like a condensed results for the first virus inactivation. So here on this side, I'm showing the control experiments when there is no plasma. So you can see the virus titer in the upstream and the downstream is basically similar. So we are not inactivating any virus. But when the plasma is operated, we can see a huge drop in the downstream impinger where we are collecting the aerosol particles. So this is almost more than 3.5 log reduction, and it is below the detection limit of the assay method that we use for our experiments. So it is no longer infectious. So interestingly, another point was the inactivation results were completely independent of the plasma power that we used. So we used basically 35 watts to 130 watts. And for all the powers, we could see the similar effect on the virus. So this means that we could anticipate the plasma to be effective even at lower power. So we can see like how the trend goes. We also performed RT-qPCR to determine the total gene concentrations in both up and downstream of the plasma reactor. So as you can see, for control experiments, we don't lose any virus particles. When the plasma is operated, we can see only a slight reduction in these gene concentrations, which might be due to some dilution effects and losses to the walls of the plasma reactor. So this suggests that most of the virus particles were inactivated by the plasma. So finally, we wanted to take a look at the possible mechanism, basically what kind of reactive species are enabling inactivation. So the exposure of the virus particles to these long-lived species, such as ozone and hydrogen peroxide, it's too short to be effective. So 3 seconds is nothing for ozone and hydrogen peroxide, because in literature, we find that it takes tens of minutes at high concentration of ozone and hydrogen peroxide to inactivate PERS virus at least. So we looked at other reactive nitrogen species. One of them is the peroxynitrous acid, and their chemistry is known to inactivate virus at low pH. So a recent plasma droplet modeling study suggested that the pH in these plasma treated droplets could be as low as 1.5, and the concentration of these peroxynitrous acid in those droplets is similar to what is required for inactivating virus in solution. So we could say that peroxynitrous acid could play a role in this inactivation. Finally, we considered the effect of short-lived species. Now, since the droplets are in direct contact with the plasma, the importance of short-lived species become paramount because the influx of these species into the droplet containing virus is much higher as compared to the long-lived species produced by, say, remote or indirect treatments. For example, I'm showing here a case of OH radicals, hydroxyl radicals, which is very short-lived, and they are highly reactive. They can react with organic compounds at rates which are much higher as compared to, for example, say ozone. So OH could penetrate. So basically, the penetration depth of OH into these droplets is limited, but the penetration depth can go up to 10 micrometers, which is basically the droplet radius. That means that OH could penetrate and treat the whole droplet during its residence time within the plasma. And from the same modeling study, we figure out that the OH concentration is quite high. It's 2 micromolar, and this can cause oxidation of the capsid proteins of virus. So it is highly likely that the inactivation of such virus aerosols is primarily due to these short-lived reactive species. So in conclusion, we found that plasma is a promising technology for airborne virus inactivation, and the aerosolized virus can be rapidly inactivated in short time scales of 10 to 15 milliseconds. And we believe that the peroxynitrous acid and short-lived reactive species such as OH radicals are most likely responsible for virus inactivation during these in situ droplet treatments by plasma. And finally, we anticipate that these plasma processes could be an effective mitigation technology for the continued coronavirus situation, for which we need further research. So with that, I would like to conclude my poster presentation and be happy to take any questions. Thank you.
Okay, thank you. Good presentation.
Thank you.
Any questions from the audience?
Yeah, I have a couple of questions. One question maybe. Is this plasma generated under vacuum or?
No, this is an atmospheric pressure plasma, so we produce it at normal atmosphere. We don't have any vacuum processes in there.
Okay, yeah. And another quick question: they are already using this kind of technology for in the food packaging industry, I believe. Is
Yes,
that right?
yes, yeah. That's why I in my in my motivation I showed this heat sensitive surfaces. So basically, they are mostly food products. Lettuce leaves, Roma tomatoes, and chicken, some proteins. Yeah, they use it for food packaging industry as well.
Any other questions? So I can ask some questions. So practically, how would you design to use this for COVID?
I think the only difference in the at least from the experimental setup point of view, I could say that the design would be same for coronavirus, but I am not sure what kind of safety level that requires. So PERS virus is basically BSL-2. So we had level 2 certification for this virus.
Yeah,
For coronavirus, human coronavirus, maybe BSL-3 or 4, I'm not sure. But from the design point of view, we need to check or we need to prevent the emission of ozone particles into the atmosphere after we released it through the plasma reactor. So we need to have like a activated carbon filter that can trap ozone. And other reactive species, they are kind of short-lived, so they would be basically below the detection limit of any instruments before it
So
reaches
my
the
major question
standard.
is where you put this, in the HVAC system or somewhere, where you put
Yes,
this device?
we plan. I mean, if provided an opportunity, we plan to do this like experiments in conjunction with the HVAC system. So basically, in the ducts of the HVAC systems.
Okay, can you go to next slide? Maybe further next. Okay, and you have a droplet diameter, which you assume that's the virus containing droplet, right? And
So yeah, go ahead.
And we know that a large droplet, say more than 5 micron, will fall to the ground within 6 feet. So if you put your device in the HVAC system, none of those large droplets will reach there. Only small one, we call it aerosol, less than 5
Yes,
micron will reach there
I
because they
think
will
so.
float, follow the
Yeah.
airflow. So essentially, in your figures, you can cut a line there. Only the left part is relevant. If
For
you use,
example, here, somewhere here,
yeah,
less than 5 micrometers
less
can
than
be,
5
say, used for this.
micrometer is what matters because all others won't be able to reach your device.
Okay. Yeah, I think I was not part of a research which was done before this, which said that the mean diameter of these PRRS virus, at least aerosols, was 2 micrometer plus minus 1. So that was good enough for this pilot project. But I think for coronavirus, yeah, it needs to like comply with the fact that we have larger particle sizes as well, more than say 5 or 10 micrometers,
We
which
have,
also
but
make us
they
like,
falling on the ground very quickly. So
yeah. So
unless
I
you
think,
put a reactor near the mouth of that person, those particles won't actually enter your device.
yeah, I mean, this is mainly for, so another thing that we were motivated while doing this project was in confined spaces, for example, where we have like airflow circulation, cruise ships, airplanes, hospital wards, where there is continuous air circulation and the refreshing rate is close to 5 to 10 minutes. So we can have the single pass device in the HVAC systems where we can at least check some virus particles which are below these droplet size of say 5 or 10 micrometers. But yeah, of course, if there are bigger particles, they will settle down on the ground, and then you would need like different technology to mitigate that. Yeah.
Okay. I have more questions, but let's move on. We need to finish all the
Sure.
presentation first.
Yeah.
So,
Yeah.
Julia, you can go ahead.
Yep. Oh, this one. Okay. Okay, so COVID-19 is a global health emergency, and people who have pre-existing cardiovascular disease are in a high-risk group because they will have a very severe outcomes. Also, the invasion of the virus and through the AC2 protein, which is abundantly present in the heart tissue, will suggest that the virus affect cardiac myocytes immediately. So a previous study of the SARS-CoV-1 revealed that there are several genes, such as envelope protein, open reading frame 3A and 8A, can create the viral channels in a host human cells. And so this is very interesting because it's suggested that those proteins are very essential for virus survival, but at the same time, how we can just explain this in our research. So we found that COV1 and COV2 have a very high percentage homology in E and open reading frame protein. So when we did computer analysis and checked the protein sequence, we found that COV1 and COV2 have a very high similarity in transmembrane domain and pore sequences, which is critical for ion channel formation. So this drives us to hypothesize that virus will connect to the AC2 protein on the surface of the cardiomyocyte, make the viroparin, and express the channel on the surface of the cardiomyocytes. So this will affect the action potential and calcium handling of the cell, which eventually can evoke arrhythmias and cardiac damage and lead to sudden cardiac death. So to test our hypothesis, we use human and mammalian cells, cell lines. And we found that SARS-CoV-2 genes expressed and stably expressed in those lines. So then we decided to check the functionality of these proteins. So we found that using our electrophysiology approach, we found that 3A and E protein are capable to form potassium permeable channels on the surface of the membrane. So when we characterize those activation and inactivation biophysical properties of this channel, we found that this relation is very similar to transient outward ion current, which is endogenous in the heart. So, and just briefly would like to explain why it's so matter, because so this is action potential, so this endogenous current involved in the phase 1 and brief repolarization. So if something happened in this phase, will definitely affect the phase 2, which is involved calcium channels. And calcium is essential for forming heartbeat and muscle contraction. So our collaborative work with bioengineering department allowed us to create a prediction model. So, and we were able to mimic the condition when the additional channel will affect, to see the effect of additional channel on the action potential shape and calcium. So we didn't see any changes in the normal condition. However, if the pacing will increase, so mimic the increase in the heartbeat rate. So we see a little, not a little, but it's actually looks like we have a little changes in the shape of the action potential. However, look at this calcium transient, which is absolutely dysregulating. So what will happen if we have calcium dysregulation? It will change the beat to beat in contraction and eventually can lead to lethal arrhythmia. So in conclusion, we believe that during this waiting vaccine time, so we can try to targeting the viroparins in patients who have a cardiovascular disease and just decrease the risk of severe illness under COVID-19. Thank you.
Thank you. Very nice talk. Any questions for Yulia?
That's a little bit different from what we have in our session.
Yeah, no questions?
Yeah,
So, go
sorry, I
ahead.
had one. So like you said, those calcium ion channels are expressed by the cardiomyocytes, and that is what triggers this irregularity in the heartbeat. Is that correct?
Yeah, so this is an action potential, and it has a different phases which involve different ion currents. And this action potential will trigger the contraction through the calcium channels. So, but everything, right? So everything in balance, and if something change, even small changes in this area, right? So it will lead to absolutely different behavior of the calcium inside the cell. And since the calcium is essential for contraction, so any small changes in the calcium concentration or cycle, calcium cycle inside the cell will just disrupt the action potential and will just disrupt the cellular function. But here, so what we know that these viroparines, in our case, we tried different solutions and we found that they are permeable only for potassium. But potassium, any changes in potassium, as you found here, right? So we'll just change the calcium current in the action potential. Did I answer?
Yeah, and so you would need some ion channel blocker drug molecules to, if you want to
Yeah,
help.
that's our next step. Thank you for this question, because we know that this current, endogenous current in the heart muscle, so it has a specific blocker, which is for AP. And so we would like to try how this specific blocker will affect our current mediated through viroparines. So if it has the same activation and activation behavior, so maybe we can see improvement. So just like a shift again back the phase two, phase two, and to see the normalization in calcium transit and contraction. So also, we know that magnesium ions, which is also we use as a supplemental in our life, so can block this endogenous current. So, and we also want to try and to see will it affect and just eliminate that additional current in cardiac myocytes.
So all of these, either the virus or the addition you want to add, you deliver them through the blood, right? Or are there any other channels?
No, so the first step, we just make a plasmids and just decided to look at the behavior of these genes in mammalian cells.
Yeah, I know. That's the way in your lab.
Yeah. So it's like
I'm thinking about practically how they work for humans.
So for humans, so this is this model will just allow us to shift to the in vivo study. And in vivo study, so we are going to deliver those channels into with adenovirus. It's the next step. So then we just will use, because it's a drug approved, the FOAP, it's a drug approved drug. So, and magnesium as well. So we probably will try, not through injections, supplemental maybe. But again, so this is the future direction which we are not say.
It's okay.
No. Yeah, so this is a future direction. So we just need to think carefully what we and how we will do this.
Okay. Okay. So any dose study, like how much we need to make a difference? Dose, the DOSE. Say you want to block the channel, you want to add something, and you need a certain concentration, right?
Yeah, and so again, we know concentration which can block the current, endogenous current. So we know the concentration because this drug can affect also the potassium channels in the brain. So there is a specific concentration.
Okay.
And so first, of course, we will try on the cell lines, and in vivo, yeah, we need to look through the literature, what concentration approved in
Okay.
like as a drug.
Okay. Yeah, I think there's a long way to go. Yeah.
Yeah, but yes. So again, we're still waiting for vaccine, and we know that our university is working very hard to at least to get some stuff. But during this time, we try to find the molecular mechanism and just block this high risk probability in patients. So
yeah. Okay. So we finish all the presentation.
Okay.
Right.
Stop share.
So now we have a lot of time for further questions. If any of you have a question for each other, you can go ahead to ask.
I had one question for Gaurav. So is your plasma device, is it like portable and like you can carry it around, or is it like a huge equipment which has to be like in one place?
So the plasma device itself is portable. It's around 7.5 centimeters in length. So you can hold it in your palm. But the whole test setup was kind of 3 to 4 meters long. So it's kind of a wind tunnel testing. But the plasma device itself is portable. Actually, this plasma device was originally manufactured or originally made for treating car exhaust, so soot particles or NOx particles. But that I don't think works well. So, but we tried with the virus particles and it worked.
So what type of electrical power supply it needs?
So we had an instantaneous power of around 260 watts, but we modulate the plasma, so we can work at 10% of that power, so around 30 watts. We can go even at lower powers, but we hadn't checked.
Okay.
So in principle, you can like use that to like apply the plasma on some doorknobs or some place you want to sterilize.
Uh, with this specific plasma, I don't think, because you would need like a airflow to take the effluent, which is basically the plasma treated gas, onto the door handle. But we have different devices like a plasma jet, which can be used, but it's a localized treatment. So basically, it's a very small scale treatment that would be done using plasma jets. But using this DBD device that I showed, you would need like a supply of air to basically push the air, treated air, to onto the substrate that you want to disinfect. So we have done this using remote treatment. So we have like 2D, another of these 2D plasma source that we can use. We have tried to disinfect different surfaces like stainless steel surfaces that has a high concentration of plasma, high concentration of virus particles in there. So in that sense, it works. But for door handles, I think a little bit more work needs to be done.
On the market, there's a lot of people told me they try to use those portable purifier, and some use the bipolar discharge. And I believe some of the portable purifier have this anti-bacterial or those stuff. So how would you compare those commonly available device to the one you present?
Um, Actually, I'm not very much aware of these portable devices. I know that one from Ireland and one from Australia that made these kind of devices. Um, I'm not sure what is the elongated period of time that these can be used for, because you are not directly treating the virus particles. It's kind of a remote treatment, so you need to use it for minutes of treatment to disinfect the surfaces. But the treatment that I showed is a direct treatment where the plasma particles come in the virus particles come in direct contact with the plasma. So it takes much shorter time to disinfect the same. So the applications would be different. My device can be used for uh, air disinfection in HVAC systems, and the device that's portable and can be used or available in as commercial products can be used for disinfecting surfaces. What's basically the UVGI radiation does. So you have upper room ultraviolet radiation that takes around 5 to 10 minutes to disinfect surfaces.
Okay, so you mean yours are faster than those UV
Yes,
type?
but but the target application is a little bit different.
Okay, that makes sense. Any further questions?
So I have a question for Sunil for this fiber that you have made. So is it something that it's like a nanostructure that you manufacture? Is it like a liquid solution manufacturing, or do you make it in gas phase and then deposit it on some kind of fiber?
So it's actually by a very popular technique called electrospinning. You probably
Oh,
might have heard
yeah,
of that. Yeah.
yes,
So
yes.
in electrospinning, you can extrude out these nanofibers by applying a voltage between the source and the collector. So I collected on a rotating mandrel, a metallic one,
Mm-hmm.
which is grounded, and peel off the membrane. But essentially, we could make the membrane just by casting films of the polymer, and that should also work.
Okay, so can these nanofibers be used in textiles, for example,
Yeah.
the wearable masks? Okay.
Yeah, so they actually use this, and I think they have big commercial units. You can generate a lot of these fabric, this mask made of these fibers uh, on a large scale.
Okay. So do you know like any commercial unit that manufactures this, like 3M or some other company? Who
You mean the equipment, the electrospinning unit, or the masks?
No, these kind of masks. Yeah.
Yeah, I think they are probably also using something like this. 3M should be, because they are into these N95 and other. So probably they should be having.
Okay.
Any other questions? Okay. Gaurav, can you talk a little bit more details about how you guys did the modeling?
Oh, the modeling that I showed was from University of Michigan. That was not our work. So
Okay, I
it's
see.
basically, yeah,
Mark
we had
Kushner.
to, yes, Mark Kushner's student, I think, he did a static droplet modeling in a dielectric barrier discharge. It's a similar kind of plasma, but they use static droplets. So it might be a little different in practical sense.
Okay. Your advisor is Jordan now. Interesting.
Yeah, yeah.
Hi, Peter.
Hello. Hi. I'm way too
Hi,
late
Peter.
now.
Yeah, I was asking your student about the modeling part, but heard it's from Mark's group.
Yeah, I actually attended the other COVID one, and
Yeah.
it was basically your group. So no,
Oh, I see. I
one
see.
other person.
Yeah.
I didn't know that. Yeah.
Yeah. Because I'm thinking, because I didn't know this works. I'm thinking maybe there's something my group could do for this plasma droplet type of stuff. And I can see there's many reaction kinetics inside. But I'm actually curious, do we actually know the mechanism? I know you guys can tell, say, after the plasma, you can see the virus become inactive. But there are some hypotheses to say these chemical species or radicals take effect, and each one have what time scales. But do we actually know what happened? What reactions? Can we consider this virus as a sort of a species to react with those radicals? Do we know those knowledge in somewhere?
Gaurav, you want to comment? Or?
Oh, yeah. So from some studies, we can filter out some of the reactive species. I think the exact mechanism for at least the PERS virus is not known. For example, we have done some research on a different kind of virus. It's a feline calicivirus. So we know that from plasma jet treatment, that simulate oxygen can oxidize the protein structure of the virus, at least the capsule.
Mm-hmm.
Other than that, I think we have done some on surface decontamination using the same virus. And we know that ozone and some reactive nitrogen species, they work in conjunction to disinfect or to inactivate the virus. But if you are looking for reaction rates of these with like the organic compounds or molecules, I'm not sure if we are like aware of those reactions.
Okay, but do you think based on the existing experimental data, say laser diagnostic or something, we could possibly build some mechanism, right? Just my idea.
But there are
Yeah,
hundreds
and I'm
of
in
species. I mean,
air plasma.
Yeah.
it's, you can measure a few. Maybe you can model all, but you need to have the data.
Okay.
It's going to be challenging. I think, like correlations like what Gaurav mentioned, we can do, but, in detail, I don't know. Yeah.
Okay. I just try to see whether there's something potential promising direction to go.
Gaurav, I have one question. So when you say active virus and inactive virus, I know that like the virologists, they measure that in terms of like infectivity or plague forming units. So is that what you did essentially to know that your virus has been inactivated?
Yeah, we use this TCID50 assay culture method to determine the infectivity. So basically, the ability of the virus to infect the host cells. So that we
Yeah.
can, yeah.
Yeah. So from what I what I gathered, though I'm not a virologist, that this method is quite a tedious and time consuming method of estimating viral infectivity, right?
Yeah, it takes up to, it depends also on virus because different virus would have different assay procedures. So for at least the first virus, it takes up to 4 days to show the final results. But yeah, 3 to 4 days, I would say.
Yeah. So there is no other like less shorter duration assay to determine. Is there any
Um,
as
I'm
other?
not aware myself, so I cannot comment. But maybe Peter knows about this EMA method, uh, the light, the radiation method that can be used, that we use for the human norovirus, Peter.
Sorry, I'm not sure what you
So,
mean.
so basically, we did this EMA detection method for human norovirus, right?
Oh yeah, but this is some molecular approach.
This is molecular probing.
Yeah, yeah.
So that's what we are. So basically, Sunil is asking if there is a faster way of detecting the infectivity of virus after we treat them with plasma.
Yeah, I mean, you need to be careful because actually plasma generates chemistry that could interfere with these molecular methods as well. So what we've seen is that infectivity gives us often a much higher killing rate than molecular methods, and molecular methods are really, also counting, inactive virus. As long, I think, as you don't really destroy some of these structures that you're measuring, you still get a signal. So with norovirus, for example, I think we were able to measure with molecular methods like a 3-log reduction out of a 6-log initially. Well, for FCV, where we also have the infection, cell line that we can use to do, we were able to have full inactivation. Well, again, with the molecular method, we only got 3-log reduction. So, I think, in my opinion, it's always an underestimate. It might depend on the technique you use for disinfection, but it is clearly an underestimation of the inactivation in the case of plasma. Yeah, I think I actually have another meeting I need to run to, so I'm sorry I interrupted, but
It's okay.
at least I was able to join a little bit. Yeah, thanks. Yeah.
Okay. Okay, I think we still could have more time if you guys want to stay. The last thing is, would you guys want to form a collaboration, either all of you or some of you, to participate in the competition? Maybe I should share that slide again. So basically this one. So if yes, this Zoom meeting should provide the opportunity to discuss. So you guys can go ahead.
Yeah, I think we can come up with something.
Also, I need to remind all of you, not limited to the session groups. So if you feel someone else in other sessions you can work with, that's also okay. But for now, we only have our session people.
Yeah, so I have like a small, not like a really big proposal, but
this is
like
really a small proposal. So
yeah.
Yes.
Yeah.
It's fine.
So I showed you the couple of devices, right? The membranes one that is easy to work with because it's all just done in buffers. But the nasal devices, to prove that concept, that no, I was looking for some kind of flow system, no, wherein if we create an aerosol of these virus particles and flow these particles towards the device, flow through them, like just like to mimic how we breathe if you put the device and breathe in. So I don't have any idea of how to, run such a kind of experiment with some kind of controlled flow rates of the aerosol. So probably, I think since Gaurav is in chemical engineering, and if you have any uh, idea or any experimental setup to run such a kind of test, because in your plasma you seem to be, no,
You just need a wind tunnel, well-controlled wind tunnel. That's
yeah,
it.
Yeah, yeah. I think we have a lot of wind tunnels in mechanical engineering department. Professor Chris Hogan, his group, I think, is mostly into these wind tunnels. And the group that I collaborated with for the wind tunnel testing was of Dr. Bernard Olson. He's a particle technology and a calibration person in our department. So yeah, I mean, for example, if you're talking about, say, wearable clothing masks, for example, that can be used in these wind tunnel settings to have, for example, your nanofiber structures there, and then you can have virus aerosolized using an atomizer and sending it through and capturing it afterwards to see how much concentration of virus you capture there. So I think it can be done. I think many groups are doing probably similar kind of work as well. But not of course not with the nanofiber stuff that you talked about. But yeah, just to check the feasibility of N95 mask or KN95 masks.
okay.
Yeah.
Also, this can be done by simulation as well, if
Yes.
you
Yes.
if you
Professor
want.
Yang Strobe, yeah. So if you don't have to go for experiments and you can do it with the simulations, yeah. I think Professor Yang's group, you published one paper on modeling of this coronavirus, right? The transmission of coronavirus
Yeah, we have
recently.
2 more coming. It's still on the work. Yeah.
Okay.
So first one
And I
is
think,
general is elevator, classroom, and supermarket. Second one is about the Minnesota orchestra, and then another one about the Minnesota music school classroom.
okay.
Yeah. We also have another one which might be relevant more to medical side. That's the lung modeling. So what happened after those aerosols go inside the respiratory system? How they transport inside the lung? That's another one. That one was sponsored by medical school. And once we know the deposition, location, and the concentration, we can couple it with a host cell model, because there's a lot of host cell model like Dr. David Odie already developed some for the coronavirus interact with the cells there.
Mhm.
Yeah.
Yeah. So Sunil, if you are interested, I mean, I am not from this aerosol group, but I
Mm-hmm.
can connect you with the actual people who work on these wind tunnels and aerosol generation capability.
Sure. Yeah, I think that would be great.
Okay.
Okay. Any further discussion or this teaming stuff? Okay, if no, I think we can finish the session. So everyone did a good job. Hope you have a nice remaining of the day and week. Okay, and if you're
You too.
interested in this, thanks. If you're interested in this, go ahead, and I give you best wishes.
Just a form, I guess.
Yeah, I think I mentioned in the chat, right?
Huh?
Yeah.
I mentioned the link in the chat.
Yep.
Okay. Okay. That's all for the session. So
Thank you.
Thank you.
thank all of you. Okay.
Okay.
So let's finish the session.
Okay.
Bye.
Bye.
Bye. Bye.